Hello everyone. I'd like to introduce the most important theoretical tool in this class, which is asymptotics, and specifically here we'll be talking about big O notation. And so the purpose of this is to estimate the dominant scaling behavior of an algorithm as a function of the input size. So roughly what this means is that I want to know if I, for example, double the input size, how much longer should the algorithm take compared to the original. So that's a question that I'll look at here. And it's really, yeah, roughly, how much longer should the algorithm take? So if I double my input size, what does it take? Twice as long? Does it take 4 times as long? 10 times as long? So let's look at what I mean by that. So I'll start off with a very simple algorithm, which gets the average of a bunch of elements in an array. And so what I'll do, I'll just implement this here real quick. You know, we always create an accumulator. So this is a nice little 173 exercise. So I will say accumulator plus equals the array at index I. And then, you know, the result is the accumulator over the length of the array, right? Actually, though, I'm not going to care too much about the result here. What I'm more interested in is counting the number of operations, because that's going to be a proxy for how long an algorithm takes, right? So let me actually count the number of operations in the loop. And that's what I'm going to return here. And so I want to know about, as I increase the length of the array, how does the number of operations grow over time? How does the run time of this algorithm grow? So I should say scaling behavior, but it's also really, you know, run time or number of operations. All right, so how does the runtime or number of operations scale as the input size gets bigger? So what I'll do is I'll just run a little experiment here. It's going to be kind of trivial in this example to begin with, but so if I were to say, you know, let's just look at a bunch of different input sizes. So I'll say maybe from 1 to 100, and then I'll just get I'll just send along a random array of different sizes here. So I'll say get average of empty.random.random and random. Okay, so then if I go ahead and plot, I get a nice line. So what I'm showing here on the x-axis is the number of operations, or sorry, the input size. And on the y-axis, I'm showing the number of operations. So here the input size is just the length of the array. And I'm counting how long does the algorithm take on an array of this length. And so, well, I mean, the number of operations, so the number of things that I have to add up here, is exactly equal to the length of the array. Okay? So that example is fairly straightforward, just a nice line. But let's say that we wanted to do the weighted average. And so now I'm going to pass along weights along with the array. So this is like you're in my class and homeworks are worth what, 60%? So to calculate your final grade, I would do 0.6 times your homework score plus 0.15 times your module score, etc., etc. So here we actually have to accumulate two things. We've got to accumulate what's in the numerator and what's in the denominator. And so now, you know, so what goes in the numerator? It's just the weight times the corresponding element in my array. But then I also need something in the denominator, which is going to accumulate all the weights. And so the result then is actually going to be the numerator over the denominator. All right, but now I'm doing 2 operations for every element in the array, right? So what's the difference? Okay, so I'll say ops average. Maybe I'll plot two different things here. And so this time I'm going to call the weighted average. And I'll need to send along two arrays. So again, I'll just make some random numbers. Doesn't really matter what they are. I just want this thing to run. See what we get. So let me plot both of the results next to each other. And again, this is going to be the surprise of the century. But when we look at them side by side, well, the weighted average takes twice as long as the average, okay? So for 100 elements, we actually have to do 200 operations in the weighted average because we have to do one for both the numerator and the denominator. So, you know, you would say that the average and the weighted average, you know, the average is faster, but they scale the same. Right, so they're both lines. The number of operations that you have to do is directly proportional to the input size. So let me write an equation that captures this behavior in general. So if I'm always doing a constant number of operations for every element in my list, then I have the equation that the operations is, again, directly proportional to the input size. And so one interesting thing that falls right out of this is, okay, what if I look at the ratio of an input that's twice as large to an input of the original size? And so what I see here is, okay, I'll just plug this in. I get C times 2n over n. Sorry, over Cn. Which ends up being just 2, no matter what C is. So the upshot here is if we double our input size, we take twice as long. So that is something, no matter how many operations you do in the loop, that's something I can say about these linear algorithms. So we would say, we say this algorithm is big O of n. Because what we're saying here is, okay, what I really care about is the fact that if I double my input size, it takes twice as long. I'm proportional to n. Okay, so yeah, we were able to look at the effect of doubling input size. Another thing we can do is if we think we know what the dominant term is here, we can also look at the ratio of our number of operations to what we think the dominant term is. And this is actually really what big O is. So here, if I was to look at, you know, operations n is equal to Cn, but then I divided that by n, which is I'm saying, okay, look, we say up to a constant. This is what the number of operations is, n. So up to a constant. So if I get a constant ratio here, then I guessed correctly, okay? So an incorrect guess for the scaling behavior would be, for example, logN. So if I guess that, okay, the number of operations scales as logN, I would get Cn over logN, and it's not true that this is a constant. So I can't simplify this anymore. This is actually going to change depending on what n is. Okay. But here, regardless of what n is, my ratio between my actual number of operations and my dominant scaling term up to a constant is a constant. So that's what I mean by up to a constant. But now here's what's interesting. So consider, let's say I add a small constant to a linear number of operations. So let's suppose that the number of operations is equal to a small constant a plus a constant times n. So it's like going up here and saying, hey, actually, maybe I did 10 operations up front or something in each of these. Maybe it took me some time to get the call stack set up for the methods, and maybe I want to actually count the amount of time I had for initializing these variables. And so, I don't know, some constant, right? That happens before I even drill into the array. No matter how big the array is, I always do some amount of work right at the beginning. So what's interesting is if I look at the ratio here, I get a plus cn over n, which I can simplify to a over n plus c. And if I plot this, so I'll say a over n plus c, I'll come up with some constants to begin with. So here I'll say my x label is the input size, and the y label is actually ratio of number of operations to n, what I think the scaling behavior is. I'm going to say n's here. There we go. So what I get is this interesting curve here where, okay, so towards the beginning, this constant dominates. So if I only have a couple elements in my array, I'm going to spend more time doing this constant amount of work that I have to do than I am going through the elements of the array. But as n gets larger, this term, cn, starts to dominate this constant. And so what we see is as the input size gets larger and larger, this eventually converges to c, actually. So it's like this constant a doesn't matter anymore. All that matters in the ratio is this constant c term. So what I'm saying more formally is that the limit as n approaches infinity of a plus cn over n is equal to c. That's really what I'm saying. Like, because what happens is, if I look at this equation here, this drops to 0 eventually. Okay? So again, if what if I change the constant to 4? Okay. Well, eventually this is going to converge to 4. All right. Now, before I wrap this up, I just want to show you one more kind of example, and then I'll leave you to the couple exercises and another video that from somebody else. But yeah, let's consider. I'll call these quadratic algorithms. These come up a lot. So let's look at an example here. So what if I wanted to sum up all pairs of elements in an array? Okay. So in this case, what I'm going to do is I'm going to loop through every element in the array, and then I'm actually going to loop through every other element in the array, and then I will sum up. I don't know why I'm doing this, but just an example. I'll sum up the array at index I plus the array at index j. So these, you'll do these kind of things a lot. Algorithms that go through all pairs in a list or an array or something. So this is the general loop. The reason I start off at I plus 1 here is because I don't want to repeat pairs. So for a pair I can say, okay, j should always be strictly greater than I. And so this loop will do that. All right, so let's keep track of the number of operations. So I'll start off at 0 here, and then in the loop is when I do the work. So I'll say ops plus equals 1. So let's just return the number of operations again. And let me just I'll just grab some of the code up here. And let's look at what we see here. So here I'll say ops pairs. I'll call the sum pairs method. And okay, so I'll say sum of pairs here. So I look at this, and this curve is qualitatively different from the one we saw before. it's not no longer the case that the number of operations is directly proportional to the input size. Actually, it gets worse and worse as the input size gets bigger. So what's really going on here is we have a scaling function which is equal to some constant times n squared. And actually that's not exactly what this particular one is. I'll show you the difference in a second. But let's suppose that we had this. Okay, so now I can ask, let me go ask the same questions that I asked before. So first, what is the ratio? So what happens if I double the input size? So that's a good thing to know. Actually, I ask myself this kind of question all the time. If I know the scaling behavior of an algorithm and I just took the wall clock of how long it ran, then I can say, okay, I know it's going to take this long when I actually put in. So what I often do myself in code is I'll run some algorithm on a smaller number of inputs so I can actually time it. And say, okay, you know, if it was directly proportional, if I timed it, I say, okay, it took me about an hour on 100. So I know if I scale it up to 1,000, it's going to take me 10 hours. That's good to know. I didn't have to spend the 10 hours to know that. I could get an estimate just off of running a short example. But how bad is it here? So if I double the input size and I look at the ratio, I get C times the quantity 2n squared over C times n squared. Well, here's the problem. Now I get C times 4n squared over Cn squared. So what I see is I actually quadruple the number of operations when I double the input size. So, you know, as an example in real life, let's look at how this scales over time. You know, I timed my algorithm to take 1 hour for n equals 100 elements. And I could say, how long would it take for 800 elements? Well, I have to double this 3 times. So it took an hour for 100, so it takes actually 4 hours for 200, right? Because now when I double, I actually quadruple the number of operations. It's going to take 16 hours for 400. And then it's going to take 64 hours for 800. So every time I quadruple. So you see this is getting pretty bad. Whereas if it were the linear algorithm, and I said how long would it take for 800, it would only take 8 hours, right? Because it's directly proportional to the number of elements. So you see how much worse this is than the linear? So that's interesting there. So now what about the ratio of okay, so we think, so somehow n squared is the dominant term here. So let's look at the ratio of, you know, this C times n squared over n squared. So that, you know, you're going to see that that is a constant. So ratio of scaling function to our estimate of dominant term, which here it's kind of trivial. It's just a constant times n squared, so that ratio comes out as a constant. Where it gets more interesting is in our pairs example. Our scaling function is actually not n squared directly. It's actually n times n minus 1 over 2, if you do it out. So let me actually expand this here. So I'll say that that is actually n squared over 2 minus n over 2. So this is a little bit better than n squared. I don't actually have to go through for every row for every column. I actually save myself a little bit of work because I start j at I plus 1. And so this is a little bit faster. And so the question is, okay, well how do I do here? So if I look at the ratio C times n, well, I'll just say straight up n squared over 2 minus n over 2. What's the ratio of that over n squared? So let me plot that. So I'll plot the first term here is n squared over 2 minus n over 2. And then I want the ratio of that to n squared. So just like I did with the linear case where I was looking at, you know, the ratio of my scaling function here, a plus cn, to what I thought was my dominant term n, I'm going to do the same thing here. Oh, I think I meant to say n's instead of n. Okay, so here's kind of interesting. And let me get my labels here. So here I'm doing the ratio to n squared just to see. Okay, is this actually better than n squared? The fact that I can save a little bit of work. And so we see, yeah, for small input sizes, it is better than n squared. But eventually the ratio ends up being a half here, okay? So this is the dominant term. Eventually the n squared term completely dwarfs n over 2. So what we would say here is the limit as n approaches infinity of this whole thing is a half in this case. Okay? And if I were to throw a constant in front of this, it would be c over 2. Alright, so these are two very important classes of algorithms. The linear algorithms. Every time you got to loop through every element in some list, that's a linear algorithm. Or the quadratic algorithms. Every time you got to look at all pairs of something, that's going to be a quadratic algorithm. So we'll see a lot of sorting algorithms that are quadratic because they have to examine every pair of elements to see which one's greater than the other one. But let me give you one more example for the road. And I'm not even going to bother coding this one up here because you've seen it before, but this is binary search. So we know that binary search takes a number of operations equal to some, you know, constant times log base 2 of the input size, where the input size is the length of the array that we're searching in, right? Because we repeatedly have the length of the array under consideration, and every time we have an array, we do some constant number of steps. Like we compare the element we're looking for to what's, you know, at a particular place in the array, and then we, based on what happens, we figure out how to move the low and the high. So some constant number, the same number of operations that we do in every loop. And this is how long it takes until we get to the stopping condition when we have a length of 1 that we're looking at. And so now let me ask the same question. So what is the ratio of operations? What if I double the input size? So that's the first question I'll ask. So just plugging and chugging here, I plug this in. Get log base 2 of 2n over log base over c times log base 2 of n. So actually, with the logs, if I double the input size, I only have to take one more operation, right? It takes one more round I have to do. Just one more round I have to do, and then I'm right back to the end. So what I would say is, this simplifies to c times quantity log base 2 of n plus 1. It's going to take one more step over c log base 2 of n. And so this is basically negligible impact when we double. So that's pretty cool. So, you know, we say we double the array, we really only added one step. Okay, let me get that. Yeah. So it's about equal to 1 if n is large enough. So actually it turns out we have to square this is kind of cool. We have to square the number of elements before we even see a doubling. So if I looked at the ratio, so this is very nice. It takes me, I have to square the number of elements before I even double the runtime. So ops of n squared over ops n is approximately equal to 2. Okay, so this is coming out of rules of logs here. And then, yeah, so the upshot here is if we look at the ratio of this to logarithm of any base, whether it's base 2, base e, natural log, we're going to get a constant. So we would say the dominant scaling term here is, we would say logN, right? So just to give you another example there. And we'll talk more about all this in class. So one more thing I need to tell you before I set you loose on the exercises. So big O specifically, there's actually 5 letters we can use, but the big O is an upper bound for the scaling behavior. So what we would say is, yeah, it's certainly true that the weighted average is big O of n, right? So n is the dominant scaling term. But actually, when we use big O, it's also true that the weighted average is big O of n squared, even though n squared is worse than n, as we saw, right? So n squared scales worse as n gets larger than n does. So this is actually an overestimate of the dominant term. But this is still a true statement because big O of n is an upper bound. So we're at least, you know, spot on. So this here we would say this is a tight bound, or an exact estimate, or tight bound of the scaling behavior for the weighted average. But it's also true that it's big O of n squared. This is just not as precise. What's interesting is you say, well, why would I ever say that an algorithm was worse than it actually is? It's like I'm a sales person, I'm trying to advertise my algorithm, and I say, oh, it's O of n squared. And why would I do that? Somebody's like, oh, that's terrible. It's going to quadruple when I double my input size. Why would I do that when it was actually O of n? Well, sometimes we're not able to prove the best bound necessarily. So maybe it's easier to prove that our algorithm is big O of n squared. We think it might be better, but we're just not sure, and it's hard to prove. So oftentimes there are open problems in algorithms where it's like, okay, we have this algorithm, we don't actually know how long it takes. These things get kind of complicated, but we can prove that it doesn't take longer than n squared. So actually, that was true about one of my favorite algorithms, dynamic time warping on one-dimensional time series. So people were able to prove pretty easily that this was big O of n squared, that this problem. But then somebody discovered an algorithm that was a little bit faster than that, and then they were able to show a bound that was smaller than n squared. So anyway, just to say, big O is an upper bound. Okay, so it can be an overestimate. And I'll talk about other letters on, a couple classes later about this. Okay, now you should have everything you know for the exercises.